The square root of x plus 4 equals x. What do we know about the answers? How many roots will there be given among the answer choices? Note, they're not giving us a value answer. So can we plug in? No, that's not possible. In many radical equation problems, we can. So what do we know about square root of x plus 4? I know how to graph that. That graph is basically the square root of x graph shifted 4 to the left for the plus 4 offset, as shown. The graph of x, or y equals x, well, it's just an upward sloping line that passes at about 45 degrees through the origin, as shown. I can see from these two graphs there is only one intersection, so there's only one real root. That is going to be my answer. And by the way, if you're unsure whether it's a rational or irrational number, you can check the discriminant. That might be our second method, but watch out for that if we're using that to solve for it. For example, I could have taken the equation, I could have squared both sides, and when I square both sides, I'll end up with 0 equals x squared, putting the left side terms over to the right, minus x minus 4. Now I could run my discriminant, my b squared minus 4ac, and check for 0, 1, or 2 real roots. If I did that, I would find out the value under my radical sign, my discriminant, would be plus 1 plus 16, it's 17. The value under the radical in my solution would be square root of 17, which tells me the answer up here is one real root, and it must be irrational, because I end up with a square root term, which is irrational, in my answer. Now, if I were looking at this and I were just using my discriminant test and trying to solve, I might say, hey, this is a positive discriminant. I have 2 real roots. Yeah, but not exactly. You need to be careful. Remember, when we square radical equations, we give rise to potential extraneous or invalid solutions, which we would then have to check. So if I actually finished off my solutions, given the quadratic formula, I might say x equals the opposite of b over 2a, which is 1/2, plus or minus the square root of 17 would be my discriminant divided by 2. Well, one of those solutions is 1/2 plus root 17 over 2. That's my irrational root we see up there in red. Okay. The other solution is 1/2 minus root 17 over 2, which would be negative. That, hypothetically, if I had the mirror image of my square root down here, that would be the root there, except it isn't there because the square root by definition is only positive. So when we plug that value back in for x, so this is an invalid solution. We can check that invalid solution real quickly in pink by plugging in 1/2 minus root 17 over 2, square root of 17 over 2 for x, plus 4 under the radical. Does that equal x, which is 1/2 minus root 17 over 2 in that case? It looks complicated, but it's not too hard. 4 plus 1/2 is 4.5. Root 17 is just over 4 divided by 2, so that's 4.5 minus 2. It's a little less than 2.5 on the left side. So this is essentially 2.5. And that equals 1/2 minus 2? No, that's more like minus 2. Those are not equal. That solution does not work. Our negative solution is incorrect. There's only one real root, one intersection, as we can see from the graphical approach. By the same token, you might be wondering if 1/2 plus root 17 over 2, that does work in the equation. Well, the square root of 1/2 plus root 17 over 2 plus 4 is essentially 4.5 plus 2, or 6.5 roughly. And 1/2 plus root 17 over 2 is 1/2 plus roughly 2, so 2.5. Square root of 6.5 is about 2.5. 2.5 squared is 6.25 to be exact. So it looks like the first solution at 1/2 plus root 17 over 2, roughly around x equals 2.5 at the red mark there, does work. Okay, in this problem, we're told 5 people in a room, they all shake hands with one another. So one way we could think of this is every handshake is a pair of people. So how many ways can I choose pairs of people out of 5 people? Well, that's going to be a combinations problem. That's going to be combination 5, choose 2, which is our formula for combinations here denotes. We can plug that in. n equals 5 people, 2, r equals 2 people we're choosing. So that's 5 factorial divided by 5 minus 2 factorial divided by 2 factorial, which in turn is 5, 4, 3, 2, 1 divided by 5 minus 2 is 3 factorial, or 3, 2, 1, and then 2 factorial is just 2 times 1. 3 2 1s cancel. I end up with 20 over 2. That equals 10 different handshakes in all. That is your correct answer. Another way you could look at this without knowing necessarily combinations or permutations is to logically sort of say I have 5 people around in my room. The first person shakes hands with 4 different people. The next person shakes hands with 3 more people. We don't count this handshake again because it already happened. The next person going around our circle essentially shakes hands with 2 different people. And last but not least, that next person only has 1 person left to shake hands with. We don't count the others because we already counted those handshakes. This sums to, again, the same answer, 10 handshakes. This is essentially a triangular sequence. Don't worry about that, but it's one logical way to think through the solution to this problem. F of x minus 2 equals 2x plus 2. This one can be confusing for many students because I got an x minus 2 on the left side and I just have x terms on the right side. So what exactly is going on? Well, this requires a review of what happens in a function. Essentially, I put in some x value into an f of x function and I'll get some output, whatever that might be. Let's call that 3x squared, right? So the x in my f of x goes into the output for the function. Those are the same x's. Well, they're not here. So what exactly is going on? Well, this suggests what I'm really doing is whatever the function is, I'm putting in x minus 2 as my input into that same function, and the output they're telling me is 2x plus 2. What I don't know is what the original function was in the middle. That's the problem here in this. Note, this is not a situation where I would say evaluate f of, say, x plus 2 when f of x equals 3x squared. If that were the case, well, I just plug in f of x plus 2 equals 3x plus 2 squared, and I'd multiply it out and simplify it. That's not this question. They're already telling you this input results in this output. What is the actual function in between? So, okay, given that, how are we going to go about this? We can do a little clever substitution here. Why don't we say y equals x minus 2. So now I know f of y equals 2 times x, but I'm going to rearrange this equation up here. X equals y plus 2. So that way I can get my f of y as a function of y. So plugging in for x, that's y plus 2, and then plus 2. So my function becomes f of y equals 2, y plus 2 plus 2. F of y equals, multiplying it out, 2y plus 4 plus 2, my function value equals 2y plus 6. The function is 2y plus 6 or 2x plus 6. The correct answer here is B. One way to check our results is to plug in some numbers. So for example, suppose x equals 6 for f of x minus 2 equals 2x plus 2. That would suggest that f of x equals 6, that would be 6 minus 2, equals 2 times our x, 6, plus 2. Or, in other words, f of 4 equals 12 plus 2, or 14. All right, so we said the function itself was, f of x was 2x plus 6. What happens if I plug f of 4 into this function? Do I get the same result for f of 4? Well, that would be 2 times 4 plus 6, which is again 14. It checks. You get the same answer. Another way to think about this or check it is to think of it graphically. Suppose I had the following xy axis, and I know my f of x function, my parent function, is 2x plus 6. That would intersect here at 6, and then over here at 3 with a slope of 2. It might look like that. What is f of x minus 2? We know how to interpret that child function. It's the parent function, f of x, shifted 2 to the right. So that should mean I shift 2 to the right. I'll intersect at 1. Is that what my function is? Well, what's the intersection there? I've got a slope of 2, so the y-intercept is 2. Yes, that is, this line is y equals 2x plus 2. So f of x minus 2 is in fact our y equals 2x plus 6 shifted 2 to the right. That checks as well.